Okay, hi everybody. So this is my little intro here. So first, the Riemann zeta function, you should just remember. So first of all, this is how you write zeta, like that. And zeta of s is defined to be equal to a sum over, now we need a new variable indexing the terms of this sum, 1 over n to the s. Okay, so just memorize this. If you want, you can remember some specific values. For example, zeta of 2 is equal to the sum over all the natural numbers of 1 over n squared, which is, 1 plus, okay, I can do this, 1/4 plus 1/9 plus 1/16 plus ... forever. Oh, plus 1/25 plus ... Okay? And supposedly, we are meant to believe this is like pi squared over 6 or something like that. Maybe that's wrong. I don't know. Okay. Also, like, how is this the graph? Well, it's not. It's not the graph of the Riemann zeta function. So the Riemann zeta function has inputs, the complex numbers. That's this horizontal plane here, the complex numbers. And so the Riemann zeta function should go from the complex numbers to the complex numbers, which means it's going from R2 to R2, which means its graph lives in R4. The graph, remember, is all the pairs x comma zeta of x. And so what we do instead is, in order to visualize it, we don't draw that, but instead we draw the graph of a different function. Namely, we take some complex number and we send it to the absolute value of the Riemann zeta function at that. And so this is R. And now we have 3 dimensions, so we can put the first 2 dimensions down here, the real part of z and the imaginary part of z, and then we put the graph sort of in the last, or the absolute value in this last dimension, and we get some sort of a surface. Okay? Now, the main thing about this chapter is knowing what does it mean for an infinite series to converge. So you just need to memorize, like, if I have an infinite series, sum of the c sub n's, where I'm summing over every natural number, that means I'm thinking about something like c0 plus c1 plus c2 plus c3 plus c4 plus forever and ever. Then by definition, this means, if we say that this sum of these c sub n terms is equal to some number s, say s for sum, what this means, by definition, this equation means that the associated sequence of partial sums converges to its limit. So we already know how to say that a sequence converges. And so what we do is we take this infinite sum and we create a sequence. S0, S1, S2, S3. And so we just take the sequence of what? Partial sums. So the S sub n are a sequence of partial sums. So that we usually call them S because of the word S, or sum starts with S. And so you just need to memorize this. Like, when you write down an infinite series, what do? Well, you look at the sequence of partial sums. So first you get one number, then you get a second number, then you get a third number, then you get a fourth number, and that gives you a sequence. S1, S2, S3, S4, forever and ever, the partial sums. because our sum keeps going. Then we ask, does this sequence, the s sub n, for n in n, does it converge to some number little s? If it does, then we say that's what we mean when we write this. Okay? So that's what we mean when we say 1 over n squared sum over all the natural numbers is equal to pi squared over 6. This is the value of the Riemann zeta function, zeta of 2. That's the exponent. When we write this, it doesn't mean that this is a number and this is another number and they're the same number. It means that this is a meaningless symbol, which now we are defining by a convergence of an appropriate sequence of partial sums. Okay? And we're saying that that sequence converges to this number. Okay? And so you really need to know, just quiz yourself on this. Like, when you get, if somebody writes down this, first of all, they actually mean that we're summing over the natural numbers. Okay, I don't like this notation 0 to infinity, like n equals 0 to infinity. Sometimes they'll write n equals 1 to infinity. Because it just seems like, well, are we starting at 0 and going over all, are we adding up all the real numbers between 0 and infinity? No, we're not. We're doing something discrete. We're starting maybe at 0 or maybe at 1, and we're adding up discrete infinitely many things. And so I like to just write exactly how many terms are in the sum. Well, there's one for every natural number. But anyway, when somebody writes this down and they say this equals s, what this means is that the associated sequence of partial sums converges to its limit. Well, to say it converges means that there is a limit s. Okay? That's what this means. And so we could unpack that. What is the sequence of partial sums? Well, we need to say, what is it? What is a sequence of partial sums? Well, a sequence of partial sums is, well, for n in n, define s sub n is equal to, so we're going to define a sequence now. Remember, we used to call sequences z sub n, but now we're going to call them s sub n because we're thinking of sums, partial sums. And it'll be the sum from little, I don't know, now we have to make up a new index because here we have already used little n, so we can't write little n there. Basically, it's s1 plus s2 plus dot 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 plus sn. Whoops, that is wrong. I have to sum up these terms, so all these s's should be c's. See, you should quiz yourself on this. You'll make little mistakes like this. And yeah, now somebody could just write like a sum of the c sub j, where j, maybe they're going to write j equals 1 to n. See the little n there is how many terms. Okay, so s3 is the sum of 3 terms. That's a number. We also have to define the number s5. It's the sum of the first 5 terms. And yes, if you start with 0, then everything has to be off. But this doesn't really matter. What matters is that you know what the sequence of partial sums means. Okay, just quiz yourself on that. It's somewhere in here. Definition, all this kind of stuff. Quiz yourself. Okay. Yeah, so here's this notation. Sum from n equal 1 to m, so that this one would be s sub little m, because that is how many terms we're taking. Okay. And maybe better is sometimes people like this, where they invent this notation to mean the set of integers 1 to n. I like that notation. And then you can, instead of writing sum n equals 1 to m, you could write sum of n in this set, where you've already told people that this symbol means 1, 2, up to n. Anyway, it's up to you how you do it. What else is in here? Oh, this equal sign. How would you discover this? So when you get to this part in the book, this is sort of, this was confusing to me when I first saw it in calculus, is that how would you invent this? Well, it turns out there's a systematic way. If I didn't know that it was like this, but I was just given this expression, and I want to split it into simpler things. So what I do, 1 over n plus 1. What I notice is I would like to have a just over that or just over that. I don't want two denominators. So what I do is I say, well, what if it's some number a plus some number b over n plus 1? So I took each of the two factors in this denominator, and I split them up. And now I want to solve for little a and b. And so you can do that. Just clear denominators. So if I multiply by n times n plus 1, I get a 1 over there, an a times n plus 1 there, and a b times n there. I cleared denominators. Okay, so an plus a plus bn. And yeah, so that's sort of interesting. And so now I've got an equation that these things have to satisfy. Okay? In particular, they have to satisfy it for every n. And so let's let n equal -1. I see that I get a 0 here, and a -b there. Oh, okay, so this implies that b is -1. And then if I look at this thing and I say let n equals 0, then this goes to 0, and this stays around, and it shows me that a equals 1. So that's how I know that this number has to be a 1, and this number has to be a -1. Okay, and this now works. So that's how they get this, a 1 and a -1. And so you can do this in general if you have any expression in, polynomials. You could try to rewrite it as something over x minus 2 plus something over x squared plus 4x minus 2. And by clearing denominators and plugging in the roots of these two factors, so n equals 0 is a root of that factor, n equals -1 is a root of that factor, and that's how I found those two numbers after I cleared denominators. Okay. Just make sure you don't get confused. There's the limit of the terms that you're adding up, and then there's the actual limit of the partial sums. They're very different. So when you get to this part in the book, make sure you understand the difference here. Page 117. It's not like it's hard to understand the difference here. It's just that this is often where it's easy to confuse this if you're not thinking straight. Okay, so if somebody hands you an infinite sum of the C sub n, where it's summing over all the natural numbers, wow, okay. Then yes, you do have a sequence. You could just look at the sequence of these C's, and maybe this sequence has a limit. It might. Perhaps its limit is 0. Perhaps its limit is 4.2. But then, if you want to say, does this make sense? Can we actually add up these things? You need to form a different sequence. These, I'll call them S sub little n, where that's, we're just adding up the first, I guess, m terms, a partial sum. Okay, and then you have this new, completely different sequence. and you can ask, does this sequence converge? And then by definition, this infinite sum equals S exactly when this sequence does converge to S. Okay, that's the definition. All right, one more thing. Yeah, think about this. So I encourage you to think about this. Here's my example I like. If it's raining, that means that there's clouds. The rain had to come from somewhere. That also means that if it's not cloudy, well, then it's not raining. Because if it were raining, there would be clouds. So if there's not clouds, then it's not raining. And so actually these two are logically equivalent. So if you ever need to prove that P implies Q, you can instead try to prove that not Q implies not P. This is a logic symbol for not Q, not P. Okay. The book proves the divergence test statement. I'm going to show you an alternative proof, but I'll do that in a different video. Really, really commit these to memory. They're just going to come up forever and ever and ever. So just commit them to memory. That's the last page.